Hello and welcome. Today, we're going to pull back the curtain on something we use every single second, but probably never think about. It's this incredible, invisible dance that happens when all of our devices, your laptop, your phone, your smart TV, all try to talk on the same network without just creating a mess of digital noise. So let's get right into it. Really think about it. Right now, in your home, you could have 10, maybe 20 different gadgets all connected to the same Wi-Fi. You're streaming a show, someone else is in a video meeting, your phone's downloading updates. They're all trying to use that same invisible highway at the same time. How on earth does any message get through clearly? Well, it turns out it all comes down to some really clever rules of etiquette that were figured out decades ago. The biggest enemy we have to fight in this world is something called a collision. And yeah, it's pretty much what it sounds like. Imagine you and a friend try to talk at the exact same moment. The words just crash into each other, and neither of you can be understood. It's the same thing on a network. If two devices blast their signals out at the same time, those signals interfere, and the data just turns into a garbled, completely useless mess. This is the core problem we have to solve. All right, to really get our heads around this, let's use an analogy that just works perfectly. Think of your network as a big, crowded cocktail party. The room itself is your Wi-Fi network. Every single one of your devices is a guest who wants to say something. And the air in that room, that's the shared channel they all have to use. Now, if everybody just starts talking at once, it's just noise, right? Nobody hears anything. So how do you get some politeness, some order into that chaos? That's the real challenge, isn't it? We need to invent a set of rules for this digital conversation. We have to figure out who gets to talk and when they get to talk, and, really important, what happens when two devices do accidentally talk over each other. The path to figuring this out is a really cool story of going from total chaos to some surprisingly elegant solutions. So let's start at the beginning. The very first attempt to solve this problem was, well, exactly what you'd expect. It was the simplest, most basic idea you could have, and also the most chaotic. We'll call it the random shouting strategy. And that's pretty much it. This was the heart of a very early networking protocol called Aloha. It was like a party with zero rules. If a device had something to say, it just said it. It just shouted its data out into the room and hoped for the best. If its message happened to collide with another one, it would realize something went wrong, wait a random amount of time, and just try shouting again. You can probably imagine this didn't work too well once the party got crowded. So they tried to bring a little bit of order to the chaos with something called slotted aloha. The idea here was to chop up time into these little slots. You could only start shouting at the beginning of one of these slots. It helped a little, but honestly, it was still super inefficient. You'd have tons of time wasted, either because two or more devices tried to shout in the exact same slot, boom, a collision, or because nobody decided to talk in a slot, which is like that awkward silence at a party where everyone's just staring at their feet. Clearly, the whole random shouting thing wasn't going to scale. So engineers turned to a much more polite, common sense rule. It's something we all learn as kids, right? Listen before you speak.
This much smarter strategy is called Carrier Sense Multiple Access, or CSMA. Now, carrier sense is just the fancy engineering term for listening. The device listens to the channel to check if it's quiet. It's the digital version of pausing at that cocktail party to see if anyone else is already mid-sentence. If the room is silent, you go ahead and start talking. If someone's already talking, you wait. This was a massive step up in both politeness and efficiency.
But even with this listen-first rule, different approaches emerged, kind of like different device personalities. First, you have the impatient listener. It listens, and the absolute microsecond the line goes quiet, it pounces and starts talking. The big risk here? What if another impatient listener was waiting to do the exact same thing? Collision. Then you have the polite listener. If this one hears that the line is busy, it backs off and waits a totally random amount of time before it even tries to listen again. This is way better at preventing collisions, but it can, slow things down a bit. And this leads us to the one major flaw in just listening before you talk. What happens if two of those impatient devices listen at the same time? Both hear silence, and both decide to start talking in the exact same instant? Or what if one device starts transmitting, but its signal hasn't had time to physically travel across the network to the other device yet? The second device will listen, think the coast is clear, and bam, you've got another collision. Solving this very problem led to the huge breakthrough that really made modern wired networking, Ethernet, possible. It was a stroke of genius, and it added one more crucial piece of etiquette to our cocktail party. You need to listen not just before you talk, but also while you're talking. This amazing breakthrough is called CSMA with collision detection, or CSMA/CD. And the process is just so elegant. Okay, so first, a device listens. If it's clear, it starts transmitting. But, and here's the magic part, it keeps listening to its own transmission. If the sound it hears suddenly turns to garbled noise, it knows a collision just happened. It immediately stops talking, sends out a quick jam signal, like yelling, "Whoa, stop," to the whole room, and then waits a random amount of time before it tries the whole process over again. And this little timeline shows exactly why that listen while you talk rule is so critical. So look, at time 0, node A starts sending a message, but that signal takes time to travel. Let's call that amount of time tau. Just before this signal gets to node B, B does its listening, thinks the line is free, and starts sending its own message. Right there, their signals collide. But here's the key. Node A won't know that collision happened until the garbled noise from that crash travels all the way back to it, which takes another tau. So it can take up to twice the travel time across the whole network for a sender to be 100% sure its message got out clean. And here's a cool little detail about this whole process. A device won't just keep trying forever if it keeps getting into collisions. The official Ethernet standard says it will try to resend a packet a maximum of 16 times. And each time it fails, it waits a little bit longer before trying again. If it still fails after that 16th try, it just gives up and reports an error. It's a small but really important rule to keep the network from getting stuck in a loop. So everything we've looked at so far belongs to a family of protocols called random access. They're all about trying to manage chaos. But there is a completely different way of thinking about this problem. It's an approach that asks, instead of managing chaos, what if we could just prevent it from ever happening at all? This basically gives us two main philosophies. On one side, you have random access, the world of Ethernet. It assumes the cocktail party is always going to be a bit chaotic, so it focuses on recovering quickly when people talk over each other. It's really fast when things are quiet. On the other side, you have collision-free protocols. These assume chaos is totally preventable. They create a super strict, orderly system so that collisions are physically impossible. And this brings us to the absolute perfect analogy for this collision-free world, the talking stick. This is the whole idea behind a really famous protocol called token ring. Think about it. In a meeting with a talking stick, there's never any confusion. If you have the stick, you get to talk. If you don't have the stick, you wait your turn. Simple. No interruptions, no collisions. So how does it work? Well, a special tiny message called the token, that's our talking stick, is constantly passed from one device to the next in a circle. If a device gets the token and has nothing to say, it just passes it along to the next guy in the ring. But if it does want to send data, it holds onto the token, sends its message, and only when it's totally done does it release the token back into the ring. The result? A perfectly fair, perfectly orderly network where collisions never ever happen. The only downside? You might have to wait for the token to make its way all the way around the circle, even if you're the only one with something to say. So, from chaotic shouting matches to learning to listen first, to even passing around a digital talking stick, these are the foundational rules that built the internet. And you might think, well, our networks are crazy fast today, so this is all ancient history, right? Not really. While modern switches have mostly solved the collision problem for wired Ethernet, the legacy is everywhere. Your Wi-Fi uses a super sophisticated version of listen before you talk called CSMA/CA. That's collision avoidance. It just goes to show that even in our world of unbelievable speeds, that basic challenge of having a polite conversation never really goes away. Thanks for joining me on The Explainer.